up, Guillaume is going to tell us about how we ought to be thinking about binders.
Right, so this is joint work with Bob Atkey, James Chapman, Conor McBride, and James McKenna. So let's start with a bit of a roadmap. We're going to spend most of the time on the motivation and then the universe of syntaxes with binding. And once we have these codes, we're also obviously interested in writing generic programs over the inhabitants of the universe. And we're also interested in generic proofs, not just generic programs. Right, so we are going to start with a basic problem. We have our language T. It's a very basic language with variables, function application, and lambda abstraction. I'm not saying what variables are. This is swept under the carpet, and we'll see, we'll deal with that later. And then we have language S, which is basically the same as T, except that we also have let binders. The languages are called S and T respectively because they're meant to be a source and a target language. And our problem is that we want to write a program transformation from S to T, inlining all the let bindings. And then we want to prove that this transformation makes sense. So we want to prove a simulation lemma for this transformation. Right, so let's start with the elaboration function. So we're going to use the semantic brackets as its name. It goes from terms in the source language, and it assumes that you have an environment of terms in the target language associated to variables. Once more, I'm not saying what variables are. I'm not saying what the notion of environment is. We just have this fat arrow to give you an idea of we go from variables to terms in T. And then we deliver a term in T. And this is defined by induction on S. And we have a few different cases which are typical of any language. So if you have a variable, you look up the associated term in the environment, and you return it. If you have a function application, this is a purely structural case. So we apply the elaboration to the function and the arguments, and we use the application in the target language to put them back together. If you have a lambda abstraction, we use the lambda abstraction in the target language, and we extend the environment with the newly bound variable as the interpretation of the free variable in the body of the lambda abstraction. And finally, we do the work in the let binding case. So we interpret the body of the let in an environment extended with the interpretation of the bound term. And so I've not been saying what variables are, but I've been lying a bit. So because we call ourselves recursively in the lambda case under a new binder, the terms in the environments will need to be adjusted. So this means that if we're being completely honest, then we have to say that before we can define this, we need to prove that T admits weakening. Okay, then we want to state a soundness lemma. So we are going to say, okay, let's say we have two terms, N and S prime in the source language, and we have an operational semantics, small step operational semantics in the source language, and we say that S reduces to S prime. Then we say that we have two environments, rho and rho prime, and we have an operational semantics for the target language, and we're saying that for all variables, the term associated to that variable in rho reduces to the term associated to that variable in rho prime in 0 or more steps. Then we can prove that the elaboration of S in rho reduces in 0 or more steps to the elaboration of S prime in rho prime. But once more, I've been lying a bit. We can't say this directly. We're relying on the fact that we have the small step operational semantics, which means that we have a notion of substitution to make sense of both beta redexes and also the ones introduced by let binders. And to be able to define substitution, we actually need to have weakening too, because once more, when we have a substitution and we push it under a binder, we need to touch up the variables the variables of the terms in the substitution. So we already have to define these things before we can state the lemma. And then once we start proving the lemma, we realize there are lots of things that we need. We need some fusion lemmas between renaming and substitution, between substitution and letter elaboration. I mean, there's lots of them. We need extensionality lemmas. So if we have two substitutions with environments that are extensionally equal, then their results will be equal. And we need identity lemmas. So if we substitute with something which is extensionally the identity substitution, we get the input term. We don't need all the fusion lemmas, all the extensionality lemmas, etc. I started counting, I found 12 plus something. I stopped counting after 12 because that's way too much for a very simple lemma. So now what we want to do is to get rid of as many of these as possible generically, so that when we have this goal, we can start stating and improving our lemma as soon as possible. Right, so the grand total is that we have two simple languages. We have a problem which is supposedly easy to state, and we need to prove 4 lemmas before we can even just state it, and then we have 12 plus lemmas before we can start proving. Of course, everything is ad hoc, so if we change the source and target language, we have to change the proofs. And it's quite noisy. So if you remember, the definition of elaboration was explicit about all the structural cases. So the function application, but also you could argue that the lambda case was structural. Right, so to deal with all of this, we're going to define a universe of codes to represent syntaxes with bindings so that we can program generically and prove generically over it. But to do that, it would be nice to understand what syntax with binding is. So we are going to just consider two constructors of the simply type lambda calculus and look a bit at their core components. So to be able to define these constructors, we need to be able to store information in the nodes of the tree. And the rest of the telescope of the constructor needs to be able to depend upon the values that are stored. We also need to be able to have recursive substructures, because we're not just talking about something flat, we have a full tree. And sometimes these substructures will have extra variables in scope. So we need to be able to talk about this idea of binding extra variables in recursive substructures. And finally, we need to be able to constrain the return type of a branch. Right, so we have this list of requirements that we want, and we are going to define a data type of descriptions, which is parameterized over the type of kinds, if you will, or types, or yeah, the constraints that will show up. And then we have a decoding function that takes one of these descriptions, a way to interpret substructures, and will give you a way to interpret a tree. So the I here will be used as the type of the branch, and the list of I is just the scope. So first of all, we want to store values. So we are going to introduce a sigma constructor, which will take a set, and then the rest of the description can depend on the value of that set. So if you store a type in it, then you can reuse it later on to constrain the type of the full of the branch, for instance. And the interpretation of this sigma will be a sigma type, where we use the value stored in the first projection of the sigma to keep computing the description. Then we want to have recursive substructures, so we are going to give ourselves a constructor for this, and it will take an index and a list of newly bound variables, and the description of the rest of the telescope. And its interpretation will be a tuple of recursive substructure where we have extended the scope with the newly bound variables, and then the rest of the description. And finally, we want to be able to constrain the shape of the indices of the branch. And to do that, well, we have a token to end a description, and the only thing that we demand is that the index that's passed as an argument to the semantics of the description matches the one we require. So that's a propositional equality constraint. Maybe it will be a bit clearer if I give an example of how to represent the simply typed lambda calculus. Well, the two constructors we saw before. So first of all, we have a type of tags, and we have two such tags. We have the application tag, which stores two types, the type of the domain and the codomain of the function. And we also have the lambda tag. And then the description of the simply typed lambda calculus is a sigma type, which stores a tag. And then we have a pattern matching function. And if we're in the case of an application, we demand that we have a recursive substructure of type sigma arrow tau, and no extra bound variable, and then an argument of type sigma, and the whole branch will have type tau. And if we have a lambda abstraction, then we demand that we have a recursive substructure of type tau in the extended context with a fresh variable of type sigma, and that will give us a branch of type sigma arrow tau. Right, so now that we have these codes, we still need to take terms, because if we take the interpretation of these codes, we only get one layer of term, and then we want full trees. We don't just want one layer. So that's the usual trick when you define data types as fixed points of strictly positive functors, except that here, because we have syntaxes, we also have a notion of variable. So we don't just take the fixed point, we take the free relative monads of the functor that corresponds to a description. So this type of term is parameterized by a description, and it has variables. So this ensures that I belongs to gamma. And then it also has one layer of term where all the recursive substructures are themselves term. And so that's how we get the full trees. Right, so once we have these trees, we want to be able to program over them. I mean, you could just write programs directly, but one thing that's been quite successful in functional programming is to add constraints on the shape of your function, and then you can get results out of it. So this is a bit like the equivalent of fold for data type, except that here it's for syntaxes with binding. So you have an extra notion of scope and variables, which is taken into account. So we start with a record of constraints. So it's parameterized by a description, and it's parameterized by two type constructors, V and C. So one for values and the other for computations. And then we store in these records a list of constraints that these need to satisfy so that we are able to define the SEM function. So if we have one of these records, so if the constraints are satisfied, then provided an environment of values for each one of the variables in scope, we can, given a term, obtain a computation. Right, so then we have a large catalog of traversals which fit that pattern. So renaming and substitution can be defined generically using the semantics framework. Then let elaboration is also one of these things, and it can also be defined generically, because once you have code for your syntaxes with binding, the act of adding let binders is just a transformation of the code. So then you can also define semantics stripping that transformation away. We also have, well, not quite pretty printing, but printing with name. Scope checking is also an instance of, well, not of semantics, but of generic programming over this universe of descriptions. And we have unsafe normalization by evaluation. There are no constraints on what your syntax looks like, and no typing constraints in particular. So there's no hope of getting a generic, safe normalization by evaluation. But at least once you start working on your language, you can use this to do a bit of normalization and check that your IDs make sense. And then you can also, of course, go back to the level of considering a specific language and have specific traversals. And why would you want to use that framework still? Well, because if you know that your traversal fits into this setting, then you can use the generic proving frameworks. So CPS translation, type checking, elaboration of a scope safe but not typed language to a core typed language are all instances of these semantics. Right, and so we've paid the price of constraining our traversals to fit into our SEM framework. And as a consequence, we would like to have maybe not free, but cheaper theorems out of it. And so that's why we introduce proof frameworks that take a bunch of semantics and relate them. So we can have a simulation lemma taking two semantics as an input and spelling out what the constraints are for the results of these two semantics to be related, provided that the inputs that are passed to these semantics are related. We can describe what it means for two semantics to be run one after the other to be equivalent to a third one. That's a generic fusion result. And of course, we've defined these abstract notions, but we also have instances of them. So all the fusion lemmas I was talking about earlier, about the interaction of renaming, substitution, let elaboration, etc., can be proven generically using this framework. Right, so we're back to the roadmap. So we saw motivating example where we had basic languages and what looked like a fairly simple statement, but we had to put a lot of work to begin with to be able to state it and then to prove it. Then we saw what characterizes a syntax with binding, and the codes that come directly from this set of constraints, and then a generic notion of traversal for these codes and of proofs over these traversals. Of course, that's not the whole story. You can find all of this and more in the paper and on the GitHub repository. And we also have questions for future work. So can we do more compilation passes than just some inlining? Can we carve out a set of syntaxes that can be safely normalized? Can we have a theory of refinement between different languages? So elaboration to a core language is a step in that direction. And can we define more abstractly a subset of well-behaved typing judgments for syntaxes so that we don't just do meta theory, we also do meta theory, where we get a bunch of results for free.
All right, we have a couple questions. Surprising no one at this point. Could you adapt this to a linear or sort of substructural theory? How would that play out with your treatment of variables? Got one for you too.
Yeah, that's a good question. So yeah, I don't know. I've worked on formalizing linear logic too in a way that's nicer than just working with multisets. and it doesn't really fit the kind of constraints we have here. Yeah.
Okay. What are the limitations of the framework, or I guess the specific points that are brought up here? Can you express recursive types? Do you have a way to talk about system F or ML style polymorphism?
So so the decoding function works with lists of kinds or types or whatever they are, which means that intrinsically we can't do things that require telescopes, right? So you will be able to represent an untyped version of these languages using the framework. You will be able to represent a version that takes phases into account, but not the well-typed by construction presentation of these things. So we have a version of System F with phases. So we have two kinds, types and terms, and this way we know that substitution doesn't mix things up. But that's as far as we can go. Yeah.
Okay. Are you familiar with Marcello Fiore's work on abstract syntax with bindings?
Yeah, so that's one of the things that's discussed in
okay, there's been a question for specific points of comparison if you...
yeah, I mean, I'm not the expert in the group on that work. There's a bit too much category theory.
All right, fair enough. Suppose I had multiple syntaxes in the same language, right? Like maybe I have some syntax of literals and some syntax of types. Is there or terms? Is there an easy way to combine those? Is that along the lines of the phase distinction you were just talking about?
Yeah, I think so. I would try to use phases there.
Excellent. Thank you very much. Let's thank Guillaume again.